Okay, so we are returning to the normal distribution, or in particular, the standard normal distribution, which is a symmetric bell-shaped curve like I have on the top here. The center is always at 0 because standard means mean of 0 and variance of 1. So that's why as you see me draw this image over and over again throughout this handout and the next one, I'll always have a symmetric bell shape centered at 0. It's not because 0 is my favorite number, it's because that is the center of this distribution. We are going to make use of something called a z-score, which again is this bottom yellow formula or highlighted formula. It's x, or an observation, minus its mean divided by the standard deviation of the distribution that x came from. And x, or z, is just a distance. It's a distance whose unit is standard deviation. So let's start applying this so you could start seeing how to use it and how to interpret it. So I'm going to look at this first problem here. Foreign students often need to take a TOEFL exam in order to study English in the US. The 2011 TOEFL exam scores had a mean of 85 and a standard deviation of 3. April achieved a score of 92 on the exam. April's friend, Yolanda, took the exam a year later. So she took it in 2012, and the exam scores were centered about 90 for that year's test with a standard deviation of 5. Yolanda achieved a score of 98. In the end, we're going to want to say who did better. Now, prior to this course, what most, maybe even all of you would do is you'd say, well, 98 is better than 92. You know, April's 98 is a higher number than Yolanda's 98 is a higher number than April's 92, which is true. Mathematically, 98 is greater than 92. But what is lacking with that comparison is it doesn't account for who had the harder test. And so one way that you might look at difficulty is look at the average. And so you could realize, well, the average on April's exam was 85 versus on Yolanda's exam, it was 90. So people on average did better on Yolanda's. So a 98, a higher number, isn't necessarily surprising because based on the mean, it looks like an easier test. It's not necessarily saying who did better. You know, maybe that gap of 8 away from the mean for Yolanda versus 7 away from the mean is meaningful. But the other thing that you could look at is also standard deviation. And if it's a fairly easy test, then you'd expect people to get similar scores, meaning that the width of that distribution, the fatness, would be more narrow. So scores are more similar. Whereas if it's difficult, then there should be greater variability or width in terms of what scores are possible to see. And so we see that April's exam standard deviation was 3, pretty small. Yolanda's exam's standard deviation was 5. And so that implies, based on the mean, Yolanda had the easier test. Based on the standard deviation, she had the more challenging one because there was greater variability in scores. So since it seems a bit confusing to choose one or the other to look at, if you include them both, which the z-score does, it subtracts the mean and divides by the standard deviation. You account for all types of difficulties. And so that's what we want to do here. I am going to do part A first, which says how many standard deviations above the mean was April's score. This is just a fancy way of saying what was her z-score. And so the z-score for April, I'll put an A subscript. April,
So
sorry?
the Z in this situation stands for the difficulty then
You
of
could
the test.
think of it as, well, the Z isn't difficulty, it is how well did the person do
Yeah, yeah.
counting?
In comparison to the other test.
Well, not yet. We'll get there.
Oh, okay.
The z-score isn't, for April, isn't using any 2012 information. It's only
Okay.
using 2011 info, which you'll see as I start plugging details in.
Okay.
April's score was 85. The mean of the test that she took, the 2011 exam.
Oh,
I'm
her score
sorry.
was 92.
Yeah, her score was 92. Her score was 92. The mean of that exam was 85. And the standard deviation was 3. Yes, 3.
Also,
So
do you prefer us to ask questions at the end, or is the middle okay, or what do you want?
you could ask whenever you have the question.
Okay.
Yeah. Some people ask throughout, some kind of wait towards the end, whatever you're comfortable with. I'm fine with you asking when, when you have that question, because it may be more challenging for me, to realize what you're talking about later on. And,
Yeah.
you're like, oh, is it this problem you're referring to? So,
Okay, cool.
I'm okay with you asking, now or later, whichever you want.
Thank you.
You're welcome. So the numerator is 7, the denominator is 3. And then when you actually divide through and put it into decimal form, you've got 2.33. And it's common practice, which you'll find out shortly, to write your z-scores to 2 decimal places. I can't explain it yet, but I'll explain that when we get to that detail. So z-scores, you should put 2 decimal places, even if the second decimal is a 0. It's just good practice, good form. So that's her z-score. This means that April did 2.33 standard deviations better because it's positive than the mean. Which is pretty good. Part B asks, well, what about Yolanda? What's her z-score? So now we're focusing on Yolanda's exam. I'll put a Y subscript just so we remember what that is later on. And Yolanda got a 98 on an exam whose mean was 90 and the standard deviation was 5. So this is 8 over 5, which when you convert this into a z-score or decimal, is 1.60. So that means that she did 1.6 standard deviations above the mean. Now Z has this distribution. So what just happened is we've got Yolanda's test here, which was relatively narrow, of standard deviation of 3 and a mean of 85. That was April's exam, excuse me. Yolanda's exam is more like here, mean of 90. You'll notice that the green distribution is a bit fatter. That's because the standard deviation was 5, so it was more variable. That means thicker, wider distribution. We know that Yolanda got a 98 on her test, and that April achieved a 92. Whoop. which is about there. And so you have these two distributions. The scores, the A and the Y, don't look necessarily too far apart, but it's hard to compare them because they're coming from different distributions. And these distributions are infinite. So even though I didn't draw the lines, this blue, really does go on, and so does this one asymptotically to the x-axis. Same with green. So there is very low probability of being really, really, really high or really small. And so in order to be able to really compare these, what we do is we transform them by converting them to z-scores so that we put them both on this distribution that I have below in black. And so we see now that Yolanda was 1.6 about there, and that April is 2.33 about here. And they're both belonging to this same black distribution now. So that 1.6 and that 2.33 are distances with respect to that mean of 0, as opposed to the top distribution where the 92 is a distance from 85, and the y, the 98, is a distance from 90. And so now we transform them so that they're on the same distribution. And so now we can compare them, which is what part C is asking for. And that is based on your responses to parts A and B. I don't know what the 3 is for, but part A and B, who performed better on the TOEFL exam, April or Yolanda? And explain. And so being that we now know their z-scores, and we've got this lovely black picture here, I could tell that April performed better than Yolanda did because she was more standard deviations above the mean than Yolanda, 2.33 versus 1.6. So that's what I'm going to write. April performed better since she was more standard deviations above the mean. And this is just another way of saying had a higher z-score. And that's it for all 3 parts of question 1. It sounded like there may have been a question on some part of this, so feel free to ask now before we continue on.
Can you go back to the so they're on separate deviations or something, right? And then
are you talking about the top figure?
yeah.
They're from separate distributions, which is why
Right,
I have one axis with 2 distributions on them. One centered at 85 and one centered at 90.
Yeah, I'm just gonna copy that down a little bit.
Hmm?
How did you place them on the lower chart where it says y is like closer? Oh, so you just kind of like there's no numbers, but you put A on the right because it's more standard deviations. I see.
Yeah, I just eyeballed it.
Okay.
I have one standard deviation sketched out
Oh, okay.
here. And so I know it's greater than one by a little bit. So I just put it to the right of one
Okay.
a little bit because it's 1.6. And
Yeah.
then equal is 2.33. So I just estimated a little bit more to the right of that.
That's cool.
Thanks.
So they're on different distributions, and how did you combine them again?
What I did was we ended up converting these to z-scores. And z-scores are standard normal random variables. So a z-score comes from the same distribution, which is symmetric, centered at 0, variance of 1. So that's why I was able to put them on this one black distribution here.
You convert to a z-score?
Mm-hmm.
Yeah. Sorry, I kind of missed this part because I was in the bathroom. So z-score, is that that equation or something?
Yes, the x minus mu over sigma. Although in the long run, it would be better for you to think of this as an observation minus the mean of the distribution over the standard deviation of that distribution. Formally, it's going to be standard error, but standard deviation and standard error are similar, so I just call it a standard deviation. I'm not really going to be too picky about that terminology. The reason that I wrote it in words here is because you're going to encounter a number of formulas that look similar. They'll have this form of something minus something divided by something. And, but when you use each are different. So this is just the first one that you're seeing. And that's why I think if you remember the word form, all of them have that same format.
So we're using that equation, you convert it to one deviation or dirt.
I convert them to z-scores, which come from a single distribution.
Okay.
You know, think of it, I don't know if you'll find this helpful, and it's not something that we normally do in real life, but most of you could probably grasp this. You know, you all probably know that different planets have different gravitational forces. And so your weight on Mars is different from your weight on Jupiter, and is different from the weight on Earth. But those weights may not be very meaningful to you. You know, knowing that you are 220 pounds on Mars may not be, it won't be an easy conversion for you to be like, oh, okay, so that is my weight on Earth then. But pretend that you had two astronauts that went to different galactic bodies, and you knew one person's weight on one body and someone else's weight on another, and you can't really compare just saying, oh, who's actually heavier in real life. And so you would need to convert both of their weights to that on Earth, which you could think of as this black distribution. So now when you know, oh, well, this moon weight was this Mars weight was this, so now I know who's really heavier. And that's essentially what's going on here is you've got so-called apples and oranges that you convert into one thing that you can then actually compare.
Wait, so would you just do the z-score for the person on Earth and then the z-score for the alien on a different planet and then put them both on the same standard deviation chart? Or you said you put them both on Earth? You convert it to Earth?
I was treating a z-score as the unit conversion, getting it back into some place that you know. So for the weights, in reality, you'd want to convert them back into Earth pounds.
Yeah.
Or but you could think of it as that is what the z-score is doing, is it is converting it into the same concept for whatever two groups you're looking at, so that
Okay.
you can actually compare them.
So the mean would on the different planet would be the weight of all the different aliens. I mean, the mean of all those
Well,
aliens.
it has to be the same creature. So it would,
Yeah.
if there were many humans that had been there before, then you knew their weight, it would be their average weight.
Okay, I think I get it. Yeah.
Oh, because April had like a score of like 2.33 or something, right? Which is higher than like 1.6.
Mm-hmm. So that means that she is further above the average. April 2.33 is further above the average than Yolanda. In this case, being above is a good thing because you usually want a higher score, when you're taking a test. So an example of when that would be bad might be if you are a runner. You usually don't want to be that far above the average because a faster time is better. Other questions before we look at number 2? I forgot to put the chat open just to see if anyone's writing instead of vocalizing. All right, let's look at another and see if things start coming together a bit more. So here it says a local golf course keeps track of the scores players achieve on 18 holes. The course was designed so that on average, players would attain a score of 72 with a standard deviation of 6. Assuming scores are normally distributed, what percentage of scores should the manager expect to see above 85? So now we've got another context, and you only have one score. So this problem isn't about comparing apples to oranges per se. What we know after reading this is we know that the mean is 72. That's how the course was designed. And we know that the standard deviation is 6. What we want is it's asking for what percentage of scores, which is another way of asking what is the probability. And I'm going to let X represent scores. Should the manager expect to see above, so a greater than, the value of 85? So this is what we want. We want to find the probability that X scores is greater than 85. Looking at the information I have, I see I've got a relation to score. I don't actually have a score, but relation as in X greater than 85. I have mu and I have sigma. And I know that scores are approximately normal. So I could convert to a z-score. And so I'm going to do that by subtracting the mean from both sides. So I've got X minus mu is greater than 85 minus, and mu is 72. And then I'm going to divide both sides by sigma. So I've got X minus mu over sigma is greater than 85 minus 72 divided by 6. Now notice that the left side inside this P statement, that Z, X minus mu over sigma, is the z-score formula that you know of so far. And the right side, we've got 85 minus 72, which is 13, over 6 is 2.17. to 2 decimal places. So now we have a z-score, but it's a relationship. It's not z equals, it's z, in this case, greater than a number. And that's because we're interested in x greater than 85. So we need to figure out what is this probability. Remember that our z-score comes from a standard normal distribution centered at 0. That's what standard normal means. The value that we have here is 2.17, and that's probability is area under the curve. In this case, we want the area to the right, z greater than 2.17, which means we want to know what is this shaded region. So let me take a step back before we continue. And okay. And what I want to do is, if you haven't done it already, go into Lalima, and under resources, I posted a Z table. All right. Let me pull it up on here. So again, you're going to need this table. So please take a look at it, because it'll come up now for the next topic and for a bit of the course later on.
Wait, what's the table called?
I think I called it Z table or standard normal table.
I don't
Are
see
we
your
gonna?
screen.
Sorry?
I don't see your screen I don't see the screen anymore. Did I mess something up?
No. I wanted to show it on my laptop, but
Oh, okay.
it's gonna force me to reset, change some settings and reset. So I'm just gonna do it through my iPad. I'm just going to it, and then I'll share my screen.
Wait, is it are we gonna, like, for quizzes or tests, like, be able to use the tables or something?
If you need it now, you'll need it for that topic.
So, like, we're allowed to use those kind of stuff.
Yeah, I would tell you if there's anything, you know, what you can and cannot use, but these tables are things that you will need. All right. All right, so if you didn't find it, again, in your course, go to resources, and there's 2 tables that I posted, one for the chi-square distribution, which we had made use of a class or 2 ago. And then below that, there's standard normal table or standard normal distribution. That's the one we make use of today. I want to just for a moment show you a third thing that I posted, which is called chart, a list of common distributions. And if you haven't looked at it, this is what it has. And so you've learned most of these now. The front side are all discrete distributions: Bernoulli, binomial, hypergeometric, negative binomial, and Poisson. The second column describes what X represents. You know, so for Bernoulli, X is 1 if the trial was success, otherwise it's 0. For binomial, X is the number of successes in n trials. For negative binomial, it's the number of trials to achieve your rth success. So it essentially describes the setting. Your PMF is the third column. Your support is the fourth column. The mean and the variance are columns 5 and 6, and the MGF is column 7. So it's got all of that there. Notice there is no MGF for the hypergeometric. Does not. Yeah, that's what the DNE stands for. But a number of these we derived, like we did Bernoulli binomial and the Poisson. So the negative binomial is the only one that we didn't actually derive. And then if you continue to the next page, these are continuous distributions, which we're working our way through. You've seen exponential, gamma, and uniform so far. And today we're tackling the normal distribution. But we're going to do it without actually using the PDF that you see written there. Eventually, you'll need to know that, but for now, it's not really going to come into play. The mean of a normal is mu, and the variance is sigma squared. This is for any normal distribution. Standard normal, the word standard is going to make mu 0 and the variance 1. But in general, it's mu and sigma squared. And the MGFs are located on the far right side here. So I did want to point this out as a resource that you're welcome to look at with your worksheets. You're welcome to look at on quizzes. Of course, if I'm asking you to derive something, then you'll actually need to show how to get there. So even though the answer is on here, I'll need to see that you could figure out how to go from first principles to here is the answer on the sheet. All right, so that, again, that resource is up there and I'll leave it there. But we're going to take a look at the standard normal table, which I've got here. And I'm really only going to focus on this first page. So I'm not really going to be teaching the second one, even though it's on here. And the reason is that by symmetry, you can get everything that you need just from half the table. What I mean by half is notice that the first page, this first column has all negative values, whereas on the second page, that first column has all positive values. And so one is all your z-scores to the left of 0, and the other is to the right of 0. And since 0 is the mean in the center, it's going to be symmetric. All right, so the first thing that I want to draw your attention to is that the table comes with a graph. Even though it doesn't put 0 in the middle, 0 is in the middle because this is for a standard normal distribution. The other thing is that it puts a z on the x-axis because this is giving you information for any z-score. And that information that it gives is a probability. And you'll notice that according to the shading in this table, it's going to be the probability to the left or less than that z value. So those are certain details that any good table is going to come with a graph like this that tells you here is the information that's in this table. Then this next thing that I want to talk about is how do you use the table? So you'll notice that the first column is labeled with a z, and that corresponds to your z-scores. But I told you a few minutes ago that it's good practice to write z-scores to 2 decimal places. How many decimal places are in those z-scores?
2.
1.
There's only 1, or at least only 1 apparent. The second decimal place is that first row. So it's going to be this 0, 0, whoa. Stop it. There we go. 0, 0, 01, 02, 0.03, 0.04, up through 0.09. That represents your second decimal place. And so if we wanted to say, look at negative 3.43, you'd look at the first row with negative 3.4, and then you would go over to the column with, what I say, 343, is that what I said? I think that's what I said. Negative 3.43, you'd go from the negative 3.4 row across to the value in the 0.03 column, which should get you here to 0.0003. That would be the probability or the area to the left of negative 3.43. So let me do some more practice problems that are off the worksheet, just so we could see this in action a bit more. So we may want the probability that z is less than negative 2.71, and the probability that z is less than or equal to negative 3.16. So let's take a look at this first one. We want the area to the left of negative 2.71. So I go to the table and I look for negative 2.71. So here is negative 2.7. And if I go across two columns to the 0.01 column, I've got 0.0034. And that is going to be my area to the left, because again, this table gives us areas to the left of the z-score that we look up. So that's going to be 0.0034 again. So now I want the area or the probability less than negative 3.16. So I go back to this table and I look for negative 3.1. Which is here. And I go to the column with the 0.06. So I have 6 as the second decimal. And that will be over here, 0.0008. And again, this is the area to the left of negative 3.16. And I could also do the probability that z is less than or equal to, let's do negative 0.55. So we go to the table and we look up negative 0.5 for the first decimal place, which is here. And then I want to look under the 0.05 column. And that's I find 0.2912. So that is the area to the left of negative 0.55, 0.2912. Right, so those are probabilities to the left of a negative z-score. Because again, the table's graphic says these are areas to the left of a z-score, and that particular half of the table has negative z-score values. And so that's why you could just look up the value directly. But then you might encounter, let's say, the probability that z is greater than negative 2.71. Let's say greater than or equal to. And so if you look up in the table, 2.71 or negative 2.71, you're going to see 0.0034. And you may just jump to that answer. But if you do a sketch, and you realize this is the area to the right of negative 2.71, and I know I want to the right because the probability is z greater than or equal to negative 2.71. Looking at this, you should ask yourself, well, does that look like 0.0034, just 0.34% of the total area? Remind me again what the total area underneath is.
1.
1 or 100%. And so you should look at this and realize, well, it's got to be pretty big because I know that 0 is in the middle. So 0.5 is the area to the right of 0. And this is shaded even more than that. So it's got to be greater than 0.5. 0.0034 must be this region here, which is what we got for that first part. So if you know this left tail, how can you get the right side?
1 minus.
What's the name of that rule?
Complement.
The complement rule. And so using the complement rule, we've got 0.9966. And so this is where drawing pictures can be really helpful, just to make sure that you don't make a mistake. Let's do a few more of these cases. Right, can someone tell me what is the probability that z is greater than negative 0.55?
Point 7088.
And so whose voice was that anyway? I missed it.
That was Kiko.
Kiko, hey Kiko. And so Kiko may have recalled in the top right here that we had the area to the left and done 1 minus 0.2912 in order to get the area to the right, which is what the problem is asking for. And this is 0.7088. And then this last one is a fresh one. We didn't do this one at all yet. And so I just want to see, how you guys fare. Try to give it a shot and get the answer for the probability or the area to the right of negative 1.23. And just in case you don't have the table, I'll put the table up here. Again, that z-score was negative 1.23.
Wait, so the reason why you have to take the complement if you're doing a greater than probability is because the table says it's for everything less than something?
Mm-hmm. Yeah, the table says the probabilities you find here are to the left. You know the total area underneath is 1. So if you want the area to the right, subtract off the left. What's to the left of 1?
Is it 0.8907?
It is, yes. So that came from looking up negative 1.23. So you're looking at the negative 1.2 row and the 0.03 column. And you should get 0.1093. But then you should remember, well, that's the area to the left. So I want to remove that 0.1093 from 1 in order to get 0.8907. So just over 89% is the area to the right of negative 1.23.
But what about, does that include the center? Because if the probability on the left is 0.1093, and then we're talking about the probability to the right, are we missing the probability at exactly 1.23?
No, because
Does the chart include that?
it does, yeah. So the probability z greater than or equal to is exactly the same as the probability of z greater than negative 1.23. Both of these are going to have the same answer. So that equal part is impacted, not for the continuous case. It is important for discrete distributions, but not continuous. And what you may have encountered in web work is for a continuous case, it asks what's the probability x equals an explicit number. And I'll just say negative 3.11. And so when it's a strict equality and it's a continuous distribution, this is always 0. And the reason it's easiest with a uniform example. So let's say we were looking at this area here. Probability corresponds to area under the curve. And right now, this shaded region is the area between two values. And with a uniform distribution, that line is supposed to be horizontal. I know it's got a little slope, but it's supposed to be horizontal. And so for a uniform distribution, it's pretty easy because as you saw 2 classes ago, that's just going to be an area of a rectangle, which is just, height times width, length times width, whichever way you want to view it. And the height here is always the same. But imagine that I was shrinking the width. And so as it gets smaller, the area is getting smaller. But as B essentially approaches A, or as I'll call this x0, and this is sum x0 plus h. So as h gets smaller and smaller, closer to 0, so that your width is essentially 0, that rectangle is pretty much height times a width of 0, and the probability is 0 for continuous distributions. And so graphically, it's easier to understand why an exact probability in a continuous case is 0, which is why having a greater than or equal to doesn't change it, or less than or equal to come up to the same thing.
Okay. Makes sense.
Great. All right, so we did 2 cases here. We did areas to the left of negative. We did areas to the right of negative. But you may encounter positive ones too. So let's do some of those, such as the area greater than 1, or the area greater than or equal to 0.25, just come up with a few different ones here. And so I do a quick sketch. I know it's symmetric, it's bell-shaped, centered at 0. 1 is over here, and I want this area. And then I go to the table. And I look for a z-score of 1, but this, oh, there we are. So I look for a z-score of 1, but this side, this table only has -1. And so when I look for -1.00, I get the value of 0.1587. And I go here and I say, okay, well, -1 is here. And this region, according to the table, is 0.1587. How does the blue region compare to the black one?
It's the same.
Equivalent.
Yeah, they should be the same by symmetry. I mean, my picture is pretty good, but you know, if it were perfect, it would be exactly the same. So by symmetry, I know that this is also 0.1587. And so that's my answer. That's what I was looking for, was the area to the right of a positive number is what we just saw, the same as the area to the left of the -1. And so I'm fine if you learn this algorithmically. I know a lot of people are like, oh, if it's greater than positive, make it less than negative, and that'll work. I think it's easier to really understand it so that sketching a picture, you should always be able to get to the answer. And so that's why I did the picture first. I didn't just jump to the algorithm. It's not my recommended path of learning. And so the probability is z greater than or equal to 0.25. Again, you could do the picture, or you may just remember this is the probability of being less than or equal to -0.25 by symmetry. And this is a negative z-score with a less than probability, which is exactly what the table gives us. And so when you go to the table and you look up -0.25, I am finding 0.4013. So about a 40% chance of having a z-score of more or equal to 0.25. Try your hand at the next one. The probability z is greater than 2.03. 2.03. So Kiko, I think you're off a column. Take a look again, you're close. Remember that that first non-z-score column is 0 for your second decimal place. You want 3 to be your second decimal place. Oh, there you go. And that is 2.23. Yeah, that's what you should find, 0.0212. So the area to the right of 2.03 is 0.0212. So we've done areas to the left and right of negative, area to the right of positive. Now we've got area to the left of positive. Anyone know how to get this? I want the area to the left of positive 2.03.
E1 minus, oh yeah, Kiko said it.
I know he's fast, but you were getting it. That's that's great. Yeah, so you'd have to use the complement rule. 1 minus 0.0212 is 0.9788. And so almost all the area is going to be in this region. And the most common question I get often is, how do you know when to subtract from 1? And more than how I know, but how I'm able to tell. If I'm ever uncertain, I just do a sketch. That's why I do a quick, again, bell-shaped symmetric distribution about 0. I put the z-score I'm interested in, 2.03, and then I shade in the area of the region that I want to find. And when I look at this, if I just look up in the table and I get 0.0212 and I think, okay, well, does that look like just 2%, 2.12%? You should quickly say, no, that doesn't seem reasonable, because that's a lot of shaded area for this distribution. And so this number must be this small piece here. But I want the yellow part, which means I need to remove that white piece from 1 or 100%. And so if you happen to be in that group where you're not confident in how we've been getting some of these probabilities so far, draw these pictures and think about what side, the left side or the right side of that z-score, does that value belong on? And figure out, well, what side do you actually want to know? And that's given from the P statement. So a less than or equal to means left side, and a greater than or greater than or equal to means area to the right. All right, let's do a few more practice of this style. And I'll give you a minute or so to try to tackle these two. So see if you could get the areas for the probability z less than positive 1.61, and the probability z less than 3.33. And I'll go back to the tables.
Sorry, what were the numbers again?
1.61 and 3.33.
Oh, it's greater than that?
No, these are both less than probabilities. And remember that this table is available to you on Lalima under resources. It's table : standard normal distribution. So while I'm happy with you looking on my shared screen, it would be great if you actually know where it is and can find it on your own. All right, so I see responses from Clark and Kiko so far. And at least for the first one, guys, you have complements of one another. And so one of them I trust is right. Let me just figure it out myself. Yeah, one of them is right. And so see if you could figure out who has it. And then you have different answers for the second one.
Were they both less than for the question?
They were. Oh,
Okay.
okay, I see. Clark, you did, for the second one, it looks like you looked at 1.33, but it should be 3.33.
Oh yeah, I did. Sorry.
No, it's fine.
So wait, 1 point, so if it's less than some number, then you just see what the one is when it's greater than that, and then subtract that from 1.
Yes, because the left and the right are complements of one another. Clark, this should help you. If you did sketches, they should look similar to this. And these are the areas that you're interested in. And that should give you a sense of the type of value. You know, should it be really big or really small that you should get for these two problems?
Yeah, I was looking at, I thought it was negative 3.33. So it's just 1 minus the answers I gave them.
Mm-hmm. Yeah. And so this will be 0.9463. And this one, 0.9996, I believe.
Yeah.
Wait, it's not 0.0537?
Because if you look at this picture, 0.0537 or 5.37% looks like this small piece here. It doesn't look like the really large black section.
Because the chart is negative and the numbers are positive.
Mm-hmm.
Wait, but I thought, because for the previous one,
Mm-hmm.
you did, z is greater than 2.03, and then you did z is less than that,
Mhm.
and you did one minus that thing to get 2.03 to get that. So I thought you had to like, for z is less than 1.61, you had to first find z is greater than 1.61 and then subtract that from
Mhm.
1.
Yeah, an area that z is greater than 1.61 is that 0.0537. That piece. And if when you do 1 minus that, you get the 0.9463. And this
I
sliver,
thought if it's a greater than probability, you have to go 1 minus
mhm,
the negative or something. I don't remember.
we did it. This answer here is 1 minus 0.0537. And this one here is 1 minus 0.0004.
Wait, x is greater than 1.61 is 1 minus the number for negative 1.61, right?
No, because the area that you just said over here, this is negative 1.61. The area to the left of negative 1.61 is going to be the same as the area to the right of positive 1.61. So there's no 1 minus there. Because by symmetry, they're going to be the same. That's what my picture is trying to show. It's close to perfect.
Wait, what about the part where when you earlier did z is less than negative 2.71, and that was 0.0034, and then you later did z is greater than the same number, and then you did 1 minus 0.0034.
Mhm.
So I thought you had to do something like that.
We did do something like that. So to get one of them, you had to do 1 minus the other. And so for us to get the probability that z is less than 1.61, we did 1 minus the probability that z is greater than 1.61. And the probability that z is greater than 1.61 is the 0.0537, which we subtracted from 1 in order to get 0.9463.
Where the number is positive,
Oh,
it's the same thing as if it's negative, right?
I think what's bugging you, Sydney, is that the 1 minus for the negative 2.71 was with the greater than or equal to sign. But here, the 1 minus is with the less than sign. Is that what's bothering you?
I mean, I don't know. So wait, if the number is positive, it's the same thing as if it's negative, right? Because you had a z is greater than 1 is the same thing as z is less than negative 1 or something.
Mm-hmm. Yeah, that's right.
Okay, is that why it's the same thing? Why z is greater than 1.61 is the same thing as z is less than negative 1.61?
Yes, by symmetry, they're going to be the same.
Okay.
So let's see. Okay. And so we have 4 cases. We did left and right of negative, we did left and right of positive, and the only one that's left is the area between 2 values. Such as the probability that z is between plus and minus 1. So this is going to be the same as the area to the left of the positive one, or the larger one, minus the area to the left of the smaller one. And again, I'll do a quick sketch just so you could visualize it if you don't see it.
You just do 1 minus 2 times whatever the decimal that you come up with is.
For this one, yeah. You don't have to have the same magnitudes on left and right, but for this one, it'll simplify like that. And so we want this region here. And one way is to just try to get it directly, or you could realize that we can get all of this area, because remember our table gives us less than probabilities, but that's too much. I want to remove this area here, which is why it's 2 less than or left-tailed probabilities. You could do 2 right-tailed, but since the table gives you left-tailed probabilities, I just tend to do to the left. And so we need both of these. And now you guys are pros or experts at finding probabilities or single probabilities. So Kiko got 1 answer, which I believe is right. So let's go ahead and think about this. So the probability that z is less than 1. When we go to this table and we look at -1 or negative 1.00, we've got 0.1587. But that is the area to the left of -1, which by symmetry is going to be the area to the right of +1. To the right of +1, but this is to the left. So this one is going to be 1 minus 0.1587.
Aren't the tails always going to be the same, like left and right tails?
Or the one I wrote here. I think the next example I have in mind will show you that they don't have to be the same.
Okay.
Then the probability that z is less than -1, we just looked up, that is 0.1587. And this happens to simplify mathematically to 1 minus 2 times 0.1587, which does come out to 0.6826. So about 68%, just a little more.
Okay, I see. I get it.
Okay, so here's one where the magnitudes on your left and your right differ. We want the area between -0.75 and +1.32. And so if you sketch this, your region may be something like what I've got going on over here. So this is -0.75. This is 1.32. And we want to know that black region there. So you could do this again through 2 left-tailed probabilities. But I'll use this example to demonstrate another approach, which you may like. And that is, you may figure out, well, what are the two white regions here? And so the area to the left of negative 0.75 comes directly from the table. So negative 0.701, 2, 3, 4, 5. No, I'm getting 0.2266. So that is this, this piece here, 0.2266. The area to the right of 1.32, 1.3012 is 0.0934 by symmetry. 0.0934. So now that we know the two white regions and we know the total area under the curve is 1, how can you get the black region?
One minus both the white regions.
Mm-hmm. Yeah. So 1 minus the two white regions, or you could add up the two white regions first. 0.2266 plus 0.0934. Subtract that from 1. And you get 0.68 like Clark said. Let me give you a few others to explore. All right, so here's 3 more. And I'll give you a few minutes to try to solve each of these. I'm gonna pause the video here. And again, after a few minutes, when all of us try to figure these out, I will return and take some requests as to what you guys got for your answers. Okay, I know you may not have finished all 3, but hopefully at least the first one. And again, the first one was the area between plus and minus 2. All right, Kiko, I see an answer for you. Anyone agree or have a different answer? This is the probability that Z is between -2 and +2. Great. Yeah, good job, Miku, Liam. So you should get 0.9544. If you draw your picture again, you could do either of the approaches, 2 left tail probabilities that you subtract, or 2 tails that you add and subtract from 1. Either way, I'll do the tail one for this case. So when I look up -2, 0.00, I've got 0.0228. And so I know this is going to be 2 of those tails. And so when I add those 2 tails and subtract them from 1, I've got 0.9544, or just about 95%, a little more. I saw an answer for problem 2 from Clark. And does anyone agree or have something else? So Kiko, you have almost the complement of what Clark has. Miku, are you agreeing with Clark or Kiko? Okay. So let's see, and I want to do a quick sketch. So negative 0.98 might be about here. Negative 3.4 is way out here. And so the region is this part. And I see that that region is smaller than 0, meaning that 0 to the left I know is half or 50%. And this shaded region is less than that, so it has to be smaller than 0.5. And so Clark, yeah, Clark, that's how I would have been able to tell that something's off with your answer. It may be close, it may just be 1 minus that, but I know that the answer can't be a big number. It's got to be less than 50%. It may be close to 0.5, like 0.4, but it's not going to be near 0.8362. Okay. So let's see, Kiko and Miku, you got 0.1632, which is what I got. So let's go through this. And so when I look up negative 3.40, I get the number 0.0003. So that's the area to the left of negative 3.40. So that's a small piece, 0.0003. When I look up the area to the left of negative 0.98, I've got 0.1635. Right, 0.1635 is the area to the left of negative 0.98. 0.1635. And so that is all of this area, 0.1635, too much. So I want to remove that white piece to the left. So when I do 0.1635 minus 0.0003, I get 0.1632. And solving the third one is similar. It's not too different from the second one here. Did anyone happen to finish the third? 0.1314. Yeah, great job, guys. And so again, the answer here is 0.1314. The area between these two positive numbers will be identical to the area if you negated both of these, because by symmetry, that would have to hold. So you could always do that in order to solve it like we just did for the second problem here. And when you look up 1.11 or negative 1.11, you will find 0.1335. And when you look up 2.7, or its negative counterpart, you will get 0.0021. And so when you subtract the two, let's say 0.1335, I believe I said, minus 0.0021. Yeah. You get just over 13%. So that's everything that you would do or could do with the standard normal table. So I just wanted to practice it because we're going to need to be able to go from z-scores to probabilities like this and then use the table in order to solve those probabilities, which is what we need to do for the second problem on the handout that we're working on. Before I return to the handout, any questions on these examples as to how to use this table? Okay, so let's look again. We're working on problem 2 here, and we got almost to the end. We want, again, the probability that scores are greater than 85, and X represents scores. We convert that to a z-score, so this is the probability that z is above 2.17. And now that you know how to use the standard normal table, you would go and you may remember, okay, well, by symmetry, the area above is the same as the area below the negative part. So you go to look up negative 2.17. And you get a nice value of 0.015. Or only about 1.5%, if you were literally going to report this as a percentage, 1.5% of scores should be above 85. Any new questions pop up? Okay, well, let's continue on to number 3 then. It says an automaker of mid-size cars claims that the distribution of mileage for all their cars is normally distributed with mean 33 and a standard deviation of 0.7. You decide to purchase a car from the automaker and determine that it achieves 31.2 miles per gallon. How likely is a buyer to select a car from this automaker with mileage of 31.2 or less? All right, so I'm going to let X be MPGs. And what this problem is asking for is the probability X is less than or equal to 31.2. What would be your first step?
Find the z-score of the car.
Yeah, convert this MPG into a z-score statement. So I want to know, this is the probability that z is less than or equal to what? So figure out what that z-score is and let me know. Yeah, Kiko, that's exactly what you should get. So you should get negative 2.57. If you are not finding that value, Nico did 31.2 as the observation minus the mean of 33 divided by the standard deviation of 0.7 to get that number. So that's where it came from. And Clark went ahead and said, hey, that's a z-score and it's a probability, so I want to use the table. And Clark and Kiko went and used the standard normal table, and they got 0.0051 as their answer, which means it's really unlikely to get that much MPG or less from this dealer. There's only half a percentage. There's one more problem left. And so I'm going to give you a minute or two on your own from scratch. So I'm not going to start you off here to see if you could finish this problem to the end. Yeah. Well, I'm not saying I base these off of real ones, but the idea holds. Okay, so I know some of you may need more time for number 4, but I do see a response. Kiko got 0.3272. Anyone else happen to finish and get same or different? Miku, same. Okay. So let's check it out. It says the weight of adult males is normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. What is the probability that one randomly selected adult male will weigh between 165 and 190 pounds? So that last statement means that the probability we want to find is this. The probability that X is between 165 and 190. When you convert this into a z-score or a z-statement, you convert the left side and the right side separately into their own z-scores. So 165 minus 172 divided by 29 will give you negative 0.24. 190 minus 172 divided by 29 will give you 0.62. All right, so again, convert each bound of X, the left and the right side, to their own z-score. And then make sure you put those z-scores in their right place. The lower value on the left, the bigger value on the right. Good job, Liam. And then from here, it's practicing what we just did on the side, which is the area between a positive and a negative z-score. And when you use your table, you should get 0.3272. And so negative 0.24 you will find in the table, negative 0.62 you will find, and you'll have to manipulate in order to get an area with respect to positive 0.62. But then using any one of the two approaches that I demonstrated, you should be able to get at the answer of 32.72%. Clark, I'm not sure where your number came from.
Is it the complement again? I keep doing that. Let me see. Hold on.
It's not the complement of the answer.
Oh, so I got 0.24, negative 0.24 was the z-score for the first one, and then that got me 0.008. And I thought that was like the probability of less than 165.
Clark, was that 2 zeros or 3 zeros? 0.0.
2 zeros, 0.008. for a z-score of negative 0.24. Is that wrong?
I think you might have done a negative 2.4.
Oh,
Yeah. Yeah, so negative 0.24, which is
okay. My bad.
0, 1, 2, 3, 4 is 0.4052. That's this region here, 0.4052 is the area to the left of that. And then 0.62, the area to the right. Is 0.2676.
Yeah, I got the right answer. I just got the wrong row.
Ah, okay. And so adding these up, subtracting from 1, will give you that middle part with the question mark there. And again, this is just one of the 2 ways to do it. So I know a lot of times students like this method more. And that's it for the examples on this handout. Any questions? All right, if not, I just want to introduce the next handout. So we're not gonna really get to do any of the problems yet, but I just want to lead into it. It's the last one for the continuous aspect of the chapter, of the course. And it'll be a small step to what we just did. So we just practiced z-scores, or the first formula that you've encountered for a z-score. And that's where you're working with an X. An X is a single observation, like a car's MPG, or a one golfer's score, or one student's exam score. But a lot of times you're not going to be dealing with an observation. You're going to be dealing with a group of observations, like 5 or 8 of them. And so rather than convert each observation to a z-score, you could convert a summary statistic into a z-score. And the summary statistic here is X bar. And X bar is your sample mean. So you just dealt with mu quite a lot. Mu is your population mean. You've seen mu before with like the expected value of X, E of X. And so that is when you have the mean or average of the entire group of interest, like the GPA of all UH Manoa students. Whereas X bar would be the GPA of my province stat class, of UH students. So it would just be a subset. So X bar and mu are both means, but they come from different groups. One is the population, which would be where mu comes from, and X bar comes from the sample, or the subset of the population. When you're converting X bar, an average, into a z-score, you'll notice you still subtract mu, but you divide by something a little different than just sigma. You're dividing by sigma over root n. And that's because this is coming from a famous theorem called the central limit theorem, which essentially says that regardless of how X is distributed, if you know it comes from a distribution with mean mu and standard deviation sigma, then X bar will be normally distributed, and it will have the same population mean of mu, but it's going to have less variability. It's going to be sigma over root n. So that's what the central limit theorem says. And that's why the z-score changes a little bit when you're converting an X bar instead of an X. And so I'm going to leave you with that thought. If you want to try to tackle any of these problems on the side to see if you get it right for the next class, that's fine. You're welcome to just wait until Thursday. I'll definitely tackle it then. But that's where we're heading next. So we're going to finish central limit theorem, and then we'll start the next chapter, which is going to get into conditioning. So this is, you've done probabilities, you've done distributions, you've done expected value, but you haven't really done too much of conditional probabilities. You haven't done any conditional expectation. So what is the expected value of X given that Y is this value? And so that's where we'll be moving for the next class and next week. All right, any last minute questions? There's about 5 minutes left, so I'm happy to hang out. I'm gonna stop the video in just a moment, but I'll tackle any questions that you may have.